All right, now that we have introduced the idea of electric flux, we can discuss the topic of Gauss's law, which is an incredible tool that we can use to figure out the electric field in certain situations. So, to introduce Gauss's law, I am going to go through an example here where I am going to figure out the electric flux through this sphere that's been drawn, and my charge distribution is just this point charge here at the center. And so you can see on the surface of the sphere the electric field vector points radially out, and so it points in the same direction as the normal vector to the surface. All right. So over here, I've got the reminder of what the electric field due to a point charge is, and the definition of electric flux. That's the integration of the electric field dotted into the infinitesimal surface area vector, and then integrated over the entire surface. And again, E is the same direction as the normal. And so just from the definition of electric flux, I've got the electric field, and I've got dA. And again, since E and N are the same direction, so since this is true, that dot product E dot dA is just equal to E times dA. And then missing an equal sign there. And then the flux expression simplifies because this term, everything there is constant, so it comes out of the integral. And then the surface area of a sphere, this term right here, the surface area of a sphere is just 4 pi r squared, and r here is the radius of the sphere. So plug in that expression down below, and you see that the 4 pi r squareds are going to cancel, and this is what we're left with. That the electric flux through this surface, this spherical surface around this point charge, is equal to Q over epsilon naught. So this is essentially the essence of Gauss's law, that the electric flux through a closed surface is just essentially equal to the charge enclosed within the surface. So things to note about this picture over here on the right. Here I've got two different spheres around a positive point charge. I've got this smaller sphere and then this larger sphere. And the flux through either sphere is the same amount. Now, from Gauss's law, we would know it's just related to, it's just Q over epsilon naught. But the reason that it's the same is that for R1, the surface area of the sphere is smaller, but the electric field at that location is larger than compared to R2, where the surface area is larger. It's a larger sphere, but you're further away from the point charge, so the electric field is smaller. And it turns out, since the electric field drops off as 1 over r squared, but the area, surface area of the sphere increases as r squared, those two things just cancel out, and you end up with a constant value. So here again is Gauss's law. The electric flux through a surface is directly proportional to the charge enclosed. And it's this middle term, right, this definition of the electric flux, E dot dA, and then integrate that over the entire surface. It's that middle term that essentially makes Gauss's law useful, because in certain scenarios where we have certain symmetries, which we'll talk about in a minute, we can actually solve for the electric field in a very short, quick, efficient manner. Well, okay, how do we use Gauss's law? Well, we'll take a few minutes here in this video, and then we'll spend all of class going through how to use Gauss's law. The reality is, Gauss's law, that statement that the electric flux is through any surface is proportional to the charge enclosed, that statement is always true, but it turns out it's not always useful to us if we're trying to solve a problem. If there's a symmetry that we can take advantage of, then we can use Gauss's law to find the electric field at a certain location. And so the symmetries that we have that we can take advantage of are spherical, cylindrical, or planar symmetries. And in those scenarios, if we use a Gaussian surface with the same symmetry as the charge distribution, we can effectively find the electric field produced by that charge distribution. And so I've got a spherical charge distribution. Here it's just a point charge, but you could also imagine a sphere of charge. And then I've got a Gaussian spherical surface drawn around it. Here I've got a line of charge, and around the line of charge I've drawn a Gaussian cylindrical surface. And so using this you can find the electric field essentially a distance away from that line of charge. And then over here I have a sheet of charge, and then so this is the planar symmetry, and here I'm using essentially what's known as the Gaussian pillbox, or some form of a box. So in each of these cases, the electric field is constant at the surface of that Gaussian surface that I've drawn. And since that's the case, the electric flux, no longer do you have to do an integral because things are constant at that location, and so the electric field is just a constant, and the surface area is just the known surface area for that type of geometric structure. So surface area for a sphere, 4 pi r squared, surface area of a cylinder, that would be 2 pi r for the radius, and then, or 2 pi r for the perimeter of the circle, and then multiplied by the length, and then the area of your square or rectangle over on the planar symmetry. And so what that means is that if you have these symmetries, then you can figure out the magnitude of the electric field immediately just by looking at Q enclosed over epsilon naught, and then including the area of the Gaussian surface for that particular symmetry. All right, so what does that mean? Well, we're going to look at examples in class to sort of understand exactly how we can leverage this piece of information to find the electric field for various charge distributions. All right, so let's look at one example. So here I have a uniformly charged solid sphere, and that charge is represented with this charge density rho naught. And what we want to do is we want to use Gauss's law to find the electric field inside and outside of the sphere. And so I've drawn two different Gaussian surfaces. I've drawn this red sphere to represent the Gaussian surface outside of our charged sphere, and then I've got the blue sphere, and that represents the Gaussian surface inside the charged sphere. And so over here on the right, I've just written down our two expressions. Of course, they look exactly the same for inside and outside the charged sphere. The only difference that we're going to find is that Q enclosed is different when we're inside the sphere as compared to outside, since the sphere is uniformly charged, that means when we're inside the sphere, we won't have all of the charge inside our Gaussian surface, right? Some of it will be outside of our blue sphere that I've drawn there. And so when we're outside, all of the charge is inside the red sphere, right? So we have to look at Q enclosed, and Q enclosed is simply the charge density multiplied by the volume element and then integrated over the volume, which becomes, in this scenario, just rho multiplied by the volume of a sphere, 4/3 pi r cubed. And the restriction here is that our radius for the volume has to be less than or equal to the radius of the sphere. Once we get outside of the sphere, there's no more charge. Right? Rho naught is 0 outside of the sphere. So that means if we want to calculate inside, our Q enclosed will be rho naught 4/3 pi little r cubed over, now our surface area, well, our surface is a sphere, so that should be 4 pi r squared. And then we have our epsilon naught. And so things cancel here, and I get a rho naught, an r. My 4 cancels, my pi cancels, and it looks like I just have 3 epsilon naught. And so inside, the magnitude of the electric field is rho naught r over 3 epsilon naught. Outside, same exact thing, rho naught 4/3 pi. Now instead of little r, I'm using big R, because remember, even though the radius of our sphere is being represented with little r, the charge density stops at big R. So the volume can only be as big as 4/3 pi big R cubed. And then we're dividing by 4 pi r squared epsilon naught. And so this is going to equal rho naught r cubed, which is a constant, right? That's just the radius of our sphere, and then divided by 3 epsilon naught r squared. And so the electric field outside, let's see if we can rearrange this just as a constant and then r squared. So rho naught r cubed over 3 epsilon naught, and then our r squared off to the side. And so we're essentially done right now. The electric field inside a uniformly charged sphere and outside. And the outside part should look familiar. It's a little hidden here, but Q total equals rho naught times 4/3 pi r cubed. And so if we plug that in for, so that means rho naught is equal to Q total over 4/3 pi r cubed. If we plug this into here, what we would get is that the electric field outside is Q total over 4 pi epsilon naught r squared. which is exactly what you would expect to get. It's Q over R squared. So even though the charge is uniformly distributed throughout the sphere, when you're outside the sphere, it's as though all of that charge is just located at the center, as though it's a point charge. All right.